Hi, and welcome to this introduction to TomoPlus. TomoPlus is a comprehensive near-surface solutions package designed to obtain accurate near-surface velocity models and derive long and short wavelength static solutions for land, OBN, and shallow marine seismic data. TomoPlus provides conventional and high-end near-surface refraction solutions to solve for a variety of environments. For simple geology, conventional approaches produce high-resolution results. In complex areas, conventional methods may be applied to derive an initial velocity model, followed by high-end imaging technologies such as Traveltime Tomography or FWI. We'll begin by introducing TomoPlus, then briefly review the basic theory of refraction seismology. We will highlight the near-surface methods available in TomoPlus, followed by two case studies. We'll then illustrate the main steps in a travel-time tomography workflow, and finally summarize the key functions in each TomoPlus module. Soon after Dr. Ji Zhang founded GeoTomo in 1998, he and Dr. Oz Yilmaz set about designing solutions to solve some of the more challenging problems in seismic data processing. While Oz focused on the complexities related to thrust belt geologic settings, Ji began developing GeoTomo's nonlinear travel-time tomography. Along with a selection of other methods, including GeoTomo's land FWI, GeoTomo's travel-time tomography continues to be a reliable and rigorous solution used in many processing departments around the world. GeoTomo's seismic processing and near-surface solutions are used not only by the processing groups in these international companies, but also by dozens of other medium and smaller-sized operations with over 600 users globally. GeoTomo's own geophysicists have gained tremendous experience by supporting such a wide range of software clients and having processed hundreds of service projects from all over the world. Okay, now let's review the basics of refraction seismology theory. The single layer case illustrates the basic principles of refraction seismology using a seismic source S and multiple receivers R, where a flat weathering layer of velocity VW overlies bedrock of velocity VB. In order for refraction to occur and therefore a head wave to form, VW must be less than VB. The first breaks to the left of the crossover distance XC are associated with the direct arrivals, and those to the right are refracted arrivals propagated at VB. By plotting first break times, we can derive the weathering and basement layer velocities. Extrapolating 1 over VB gives the intercept time TI, so from the equation shown, we can find the depth to the weathering layer ZW. The multi-layer case follows the same principle, where the velocity of each layer is greater than the one above. Again, the reciprocal of each velocity is given by the slope of the first break times, and the depth to the ith layer is computed by the formula shown. Indeed, this principle is used in TomoPlus to derive initial velocity models prior to refinement by the more sophisticated methods. Now, in practice, travel time plots are often difficult to interpret due to surface elevation changes and undulation of the base of the weathering layer and so on. The delay time method, also known as the plus-minus method, developed in 1959, enables us to calculate statics without needing to interpret a travel time plot. A static value for a shot or receiver at location D is calculated directly from the first break picks. T plus and T minus are derived as shown, and then the shot receiver static at location D is given by the equation on the right hand side. So for more details on this method, please refer to Dr. Oz Yilmaz's text, Seismic Data Analysis. Velocity inversions occur where higher velocity layers overlay lower velocity layers, for example, where anhydrites or volcanics may be present. The refractions cannot take place and the underlying lower velocity layer will be hidden. So 3 layers will appear as 2, and the thickness of the middle layer will appear exaggerated. In such cases, we need to apply full waveform inversion. Here is a summary of the model-based methods. Each method seeks to update an initial model by minimizing the difference between observed and modeled first break times, or in the case of FWI, early arrival waveforms. The GLI method uses a layer-based model and a least squares technique to minimize the difference between modeled and first break picks. Nonlinear travel-time tomography uses a grid-based model and seeks to iteratively update the model by using a non-linear inversion approach to fit the travel time curves whilst solving for non-uniqueness to the travel time inversion solution. FWI also uses a grid-based model and minimizes differences between recorded early arrival waveforms and modeled waveforms generated by acoustic finite difference modeling. Now we will summarize the near-surface methods available in TomoPlus and show a comparison of results between the basic methods versus travel-time tomography on a synthetic model. So these are the commonly used methods in TomoPlus, listed in order of increasing geologic complexity. Basic methods include delay time and GLI 3D, which apply to flat layers with local constant velocity and dipping layers with constant vertical velocity, respectively. Non-linear travel time tomography is required for more complex situations where vertical velocity gradients and pinch-outs are present. Where inversions are present, FWI is required. Joint travel time tomography FWI can help solve non-uniqueness in some complex environments. As well as providing higher resolution results, the multi-physics solutions help in areas of sparse seismic coverage. So this modeling exercise was designed to compare delay time and GLI 3D to travel time tomography in the presence of dipping layers and a vertical velocity gradient. And the initial model is shown at the top in the center. Synthetic shot gathers were created on which first breaks were picked, then a model and a set of statics computed for each of the methods. Note the comparison between the models produced by each method and the initial model. Statics calculated from the true model are shown by the blue curve, and the green curve shows statics calculated by each of the methods. The travel time tomography is the only method which closely reproduces the dipping layers, velocity gradients, and the correct statics. Next, we will review two case studies. The first compares seismic data processing results after applying statics derived from the Intercept time method that we showed earlier, the multi-level case, and then travel time tomography. The second case study compares near-surface models built using travel time tomography versus FWI in an area of complex shallow geology with velocity inversions. In the first case study, we see how results obtained using near-surface methods derived from the Intercept time method and travel time tomography produce quite different results in the processed seismic sections. The area is located in the eastern province of Saudi Arabia. Karst features contribute to a complicated near surface with sinkholes and partially dissolved layers. The first breaks were picked on the shot gathers, then plotted in accordance with the Intercept time method, thereby providing an estimation of the weathering and refractor velocities at each location. The elevation profile, velocity profile, and intercept time depth velocity pairs are shown. Static corrections are computed by traveling down through the local weathering velocity to the base of the model and then traveling to the reference datum at the local refractor velocity. This is the velocity model derived from travel time tomography. Notice the model is grid-based and shows relatively rapid vertical and lateral velocity variations. An initial model was built using velocities defined by the first arrivals. Ray tracing and inversion were run until the modeled and observed peaks converged. Then the seismic data were reprocessed using static corrections computed from this model. Here is the processing result using the Intercept time method. Note the significant long wavelength pull-up in the middle of the section, showing several stacked anticlinal closures. Now, isochron mapping between interpreted horizons showed little upward thinning of these time closures, raising doubts as to their real existence in the depth domain. So further investigation was undertaken to determine whether these time closures could be caused by unresolved near-surface problems. Now, here's the processing results using travel time tomography. The anticlinal structures previously mapped were either reduced in size or completely removed by the updated statics model. So the updated results are in agreement with well data. Note the blue interpretation is carried over from the Intercept time-derived seismic section for comparison. Several structures previously designated as prospects were shown to be false structures caused by near-surface effects. The processing results using the Intercept time method. and again, travel time tomography. Intercept time, travel time tomography. So in conclusion, the near-surface modelling method has a major effect on the long wavelength solutions in areas with complex near-surface. Travel time tomography has the advantage that it can model vertical velocity gradients and rapid lateral velocity variations. It also models diving ways where refraction arrivals are weak, and generally produces a more accurate model of the complex near surface. Okay, here's our second case study. Travel time tomography for velocity estimation can be inadequate where casts, velocity inversions, outcropping refractors, and strong velocity contrasts are present. In this case study, we compare near-surface velocity models derived from 3D travel time tomography and 3D FWI. The data preparation steps for FWI are as follows. The top left shows a shot gather with a time variant gain, and top right shows the data after noise reduction, surface consistent decon and surface consistent scaling. The bottom left shows the muted shot record after a bandpass filter, and the bottom right are synthetic traces after one pass of forward modeling. Here we overlay the recorded traces in black and the modeled traces in red, showing the results after one pass of forward modeling and after 20 passes. Note where the arrow shows improvement in the overlay of the reflection events. These displays show the near-surface models derived from travel time tomography and FWI. The FWI results produce a velocity model showing greater vertical and lateral resolution of cast features and reveals the velocity inversions which are not present in the travel time inversion model. Now let's review a typical workflow using travel time tomography to build a near-surface model, then calculate and apply statics. We'll show the key steps from first break picking and quality control to the application of long and short wavelength statics. Starting with the shot gathers, we apply a linear move out, then choose a picking strategy depending on the wavelet shape and the noise levels. Because accurate first break picks are essential to building a quality near-surface model, TomoPlus provides a wide selection of picking and QC methods. Shown here is pick similarity, where spurious picks can be identified from the shot receiver maps and then directly accessed and edited. Any remaining bad picks can be removed on the travel time offset graph. When we're satisfied with our pick times, we then pick our refraction turning points on the travel time offset graph to build our initial model. At this point, we run multiple iterations of travel time tomography until the modeled and the pick travel times converge. We can QC the synthetic and the real picks overlaid on the gathers and on the travel time misfit map. We review the ray density map to ensure sufficient coverage and that the rays do not penetrate the bottom of the model. If they do, we need to increase the model depth. Once we're satisfied with all of the above, we have our final model. Top left is the model with topography displayed. Smoothing the topography gives us the floating datum. We then create an intermediate datum, typically by choosing an isovelocity surface to represent the base of the near surface. We now calculate our total statics. First, shots and receivers are moved down from their locations to the intermediate datum using the model velocities. They are then moved up to the floating datum using the replacement velocities. And this is the long wavelength static to floating datum. Residual statics are the difference calculated between the smoothed and the unsmoothed long wavelength statics after linear move out. So the sum of the two sets of statics is moved to the final flat datum using the replacement velocity specified and is displayed on the total statics map. Here is a shot gather before application of total statics. And here is the shot gather after application of long wavelength and refraction residual statics. Before statics applied and after. For those that may be interested, Xi Zhang published a paper entitled Non-Linear Refraction Travel Time Tomography, available on Geotomo's website. In his concluding paragraph, he states, A combination of the following approaches presents a high-performance tomography product: the forward ray tracing method, the inversion approach that fits travel time curves, and a non-linear method for uncertainty analysis. Now let's review the main functions of the modules in TomoPlus. Survey Map enables management of 2D and 3D projects with multiple SEG2020 files. Survey Map also tracks multiple 2D lines, automatically tying their velocity models and datums and statics at crossing points. A 3D travel time and velocity map may be created from a multi-2D line survey. TomoPlus also has a comprehensive range of SEG2020 file, project, and cluster management utilities. The Picker module contains a wide selection of options for picking and QC of first breaks. A constant or variable linear move-out may be applied, and data can be viewed and picked in the common shot, common receiver, or common offset domains. Picking strategy may be influenced by signal-to-noise and first break shapes or source type, and a variety of automatic, semi-automatic, and manual methods are available. QC functions include reciprocal area, pick density, shot misfit, and pick density. For 3D surveys, users may pick in CMP node space, on nodes, supernodes, or line subsets, whereby all traces within a specified CMP radius are output into a specified grid. In the Time module, users may display and edit picks, compare picked versus model travel times, and check errors are small, then construct an initial model by picking the turning points on the offset travel time graph. The delay time statics method is also computed in this Time module. Prep contains a wide selection of 2D and 3D signal processing tools, and users may interactively build a sequence of processing steps with selected parameters, up to NMO velocity analysis and CMP brute stacks, providing a very convenient QC of near-surface models. Wavelet extraction and signal preparation for FWI is also performed in the Prep module. The 2D, 3D imaging module contains the near-surface imaging methods, including Traveltime Tomography, GLI, FWI, various joint inversions, and multi-physics methods. The initial model is updated according to the selected imaging method. The output is the final velocity model, calculated first arrival times, and residual statics. In View M, you can view the velocity model, smooth topography to derive the floating datum, and compute the intermediate datum that defines the interface between the near surface and the subsurface. The model may be smoothed or edited, and the replacement velocity computed. At this stage, the ray paths should be examined to make sure that they do not reach the bottom of the model. View M also enables 2D and 3D finite difference modeling. Here we compute the shot and receiver long and short wavelength statics, plus the total static to final flat datum. First, shots and receivers are moved down from the source and receiver position to the intermediate datum using the velocity field from the final model. Then they are moved to the floating datum using the replacement velocity, and next they use the final flat datum using the replacement velocity specified. At this stage, you may calculate shot and receiver residual statics from travel times. The total shot and receiver statics are to be applied in the next step. Stack allows the user to input a set of pre-processed shot gathers, apply one or several static solutions, and pick stacking velocities based upon semblance. The idea is that the user can generate several different near-surface static solutions and compare them on a stacked basis to help decide which solution is better. Users may pick velocities and or stack the data based upon CMPs or super CMPs. The data can be stacked using the same velocity field for all static solutions, or by picking different velocity fields for each static solution. So in this introduction to TomoPlus, we reviewed the basics of refraction seismology, compared some of the methods available, discussed 2 case studies, reviewed a workflow for Traveltime Tomography, and summarized the key modules. So thank you so much for watching, and please let us know how we can help you with your near-surface modeling requirements. Thank you.